back off of what we ended with yesterday, sort of, telling you that, kind of bringing this whole chapter full circle in a way, because on the very first day, I told you this. I told you that the word "and" in probability means multiply. What I didn't tell you is that only works if the events are independent. And now that we know more about independence, I'm going to reinforce that. And to be honest with you, the questions that I asked you in the beginning of the chapter, when I did go ahead and just say "and" was multiply, so we'll multiply, they were independent events. So we didn't do anything wrong. I just kind of left a little detail out. So we'll jump right into this first exercise where we are given a spinner. Spinner is spun twice. So there's your two events. And that's what it takes to really have to think about independence. You have to be doing multiple events. And the question is what's going to happen on the second event affected at all by what happened on the first event? And if it's affected at all, then they're not independent. Okay? So you tell me, if I spin this one time, and then I go and spin it again, are my results on the second one, on the second spin, at all dependent on what happened the first time? No. So these would be independent events. They're two totally separate events. Nothing about what happened the first time is going to affect what happened the second time. So what is the probability that you will get an even on the first spin? And, because we know that they're independent, now we can do multiplication. A number greater than 5 on the second spin. So we're looking at the probability of an even times the probability of getting a number greater than 5. Morgan, what is my probability of getting an even number? 4 out of 8. Times. Oh, who's ready for a doozy of a question? Jay Clancy, I know, I can see it. You're ready. What's the probability of getting a number greater than 5? 3 out of 8. Good. Because only 6, 7, and 8 are greater than 5. So we just multiply. So the overall probability of this happening, 12 out of 64, and division on your calculator will give you approximately 0.19. So about a 19% chance. Okay. C has a little twist. What is the probability that you will spin a prime number and a perfect square in either order? Why is this a little bit more complicated? What's the twist? It doesn't tell you the order. So when we do this probability, this specifically meant that we were getting an even the first time, and we were getting a number greater than 5 the second time. So now we're looking at the probability of getting it's prime and perfect square. So the probability of getting a prime times the probability of getting a perfect square, or the probability of getting the perfect square first and the prime number second. Okay, so we'll look at the probability of getting a prime. How many prime numbers are up here? 2, 3, 5, and 7, right? 4 out of 8. So 4 out of 8 times, how many perfect squares are up there? 2, 1, and 4. So that's times 2 out of 8. What does the word "or" do for us? Good, Morgan. Add. And then probability of perfect square, we already said it was 2 out of 8. It's still 2 out of 8. Times probability of prime is still 4 out of 8. So we have 8 over 64 plus another 8 out of 64. So we've really opened our options, okay? We can not only just get a prime first and a perfect square second, but because it can be in either order, we've now really doubled our chances, right? Because now perfect square and then a prime is also acceptable. So you've really doubled your chances. So that's 16 out of 64, which is 0.25. If it was just prime and then perfect square in that order, you'd only have an 8 out of 64 chance. But because you're allowed either order, that opens your options a little bit, and so your probability is just a little bit higher. It's actually not a little bit higher, it's double. Okay? Sarah?
So like whenever there's going to be like an either order, it's always going to be like an or?
Or in between the two, exactly, yep. All right, next exercise. Oh, geez. Hunter, read that for me, please.
Class consists of 12 girls and 8 boys. A group of 3 is picked to give a speech. The students are picked at random. What is the probability that they will be enjoyed? It is given below to show how you calculate your final answer.
Okay. So, in general, we're looking for the probability of picking a boy, and another boy, and another boy. What is my probability on the first event of picking a boy? 8 out of 20. Now, we can work around the fact that once we select that first boy, let's say it's you, Anthony, what happens to the number of kids we're choosing from now? What did you say? Decreased by 1. Now there's only 19 kids to choose from, right? So on the second pick, what's the probability that it's a boy? There's now only 19 kids left, and how many boys left? 7. And on the third pick, if that second boy is now out of the mix, we're down another person in our overall pool, so we're only down to 18 kids, and we're down to 6 boys. And because we've changed our, our pool accordingly, we can still consider these now independent because we're changing our pool. It's not like we're going back to the original numbers, okay? So we can still do multiplication here, and when we multiply 8 times 7 times 6, we get 336 on top, and on the bottom, 20 times 19 times 18, 6840. So 336 out of 6840 would be 0.05. So it's not very likely, but it obviously can happen, right? Here was my other suggestion on this problem, but just even looking at that, I can immediately see why this isn't practical, would be a tree diagram. But watch how ugly that's going to be, because on your first event, you're going to have, this is going to be the top of your tree diagram, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 girls, and 8 boys. See why we need shortcuts? So that's just my first event, right? And then if I pick this particular girl the first time, how many branches do I have? 19 branches, right? Of the remaining 11 girls and the 8 boys. So clearly this is going to get ugly. And then each one of these, let's say I picked a girl again, each one of these is going to have 17 branches, right? 2 of the girls are gone, so I only have 10 girls and 8 boys. Did I say 17? I meant 18. So we've got 20 options times 19 per option, which is the 20 times the 19 times the 18. That's where your denominator is coming from. Okay? Does that make sense? Now, the one thing I'm thinking here, though, is, did I consider the fact that the order does not matter? Like, let's say this might particularly be, boy 1, boy 2, boy 3. But I didn't specify that it had to be specifically boy number 1, did I? Because if it was specifically boy number 1, I only would have had 1 out of 20 chances of that happening. Do you follow? So I kind of did cover by knowing that there were 8 options out of 20 that would be satisfactory. I allowed that to be any 8 of the boys. And then I allowed the next one to be any of the 7 that were left over. Otherwise, if it was a specific Austin, Jake, Anthony, I would have to go, if I wanted Austin first, I would have to say 1 out of 20. And Jake second would have to be 1 out of 19. Does that make sense? But I already had the option open to be any boy. So I've already taken into account the different orders. Okay? Ugh, probability gets so ugly so fast. It really does. I took a probability class in college, and I got confused on day 2. I thought this would be easy. Probability, what's not easy? And it was not. Next exercise, we are, say that a power generating facility has 3 primary safety switches in case of an emergency. The probability that any one of these switches would fail is 5%. But there's 3 switches, okay, for safety purposes. What is the probability that all 3 fail? Given that the switches are independent, so that's them giving us permission to do our multiply rule. So we're looking for the probability that we fail, the first one fails, and the second one fails, and the third one fails. So what is the probability that the first one fails? 5%, so 0.05. And multiplication. What's the probability that the second one fails? 0.05. And multiplication, the probability that the third one fails? 0.05. So if I multiply all those, this is what my calculator just told me. What is that? This is scientific notation. We're going to move the decimal 4 units to the left. So over once, we'll put it in front of the 1, and then we have 3 more times to fill with zeros. So that's 0.000125. As a percentage, that's 0.0125%. So that's less than 1% of a chance. Much less than 1% of a chance, even. So they put 3 safety switches there because the chances of all 3 of them failing, could it happen? It can. But you'd be really unlucky if it did. Okay? Oh, the back. I don't think... I'm going to leave off that bottom part, how many ways. I don't think we're going to have to do that. But try this first exercise on your own while I pass out the homework. And because some of you have a review sheet and some of you don't, I'm just going to leave the stack there, and so on the way out, if you want to grab it. If you need one, you can grab one. Okay, this particular table is missing our total category, right? Although it's percentages, so they should add up to 100%, but I'm gonna put them there. 100%, 100%.
One of them adds up to 103.
Oh yeah, this one doesn't add up to. $11, carry the 1, 91.
You don't have it horizontally, I think.
They don't, shoot. Oh boy, what's happening here? We might need to finish this one. This one might be confusing. I might take a video of this one and post it online. You might see 2 videos for today, because there's no way I'm gonna get through this in 45 seconds, because I think there's a lot that's going into it. So, yeah, they don't add up horizontally. So, I'll put 2 videos tonight, what we got through, and then I'll do this one separately, if you wanna see it.
Question.
And then I'll post them both, and then test tomorrow, okay? Because we don't have time for that.
Two questions. One, first, why did total